Thank you, Martin, again. Ladies and gentlemen, the organization of tunnel projects has changed in the last years. In earlier times, we had the organization that the one built the tunnels and then handed over the finalized tunnels to the operating unit. And these were two different companies on the client side. But it changed. Now, making the management more effective, we have the construction and the operation in one hand. And this brought a completely new approach how to design, construct and operate tunnels nowadays. I mentioned in my first speech that our clients would like to see a lifetime of the tunnels of 100 years. Asking the clients, what tests should we do? What would you like to see from our side? They don't have something available. What should we really test? So we said, okay, then let's learn from the past. Let's go to the tunnels which were built the last 50, 40, 30 years, but also make some tests in older tunnels. There are tunnels which are more than 100 years old, still under operation. And the question was, okay, when or how can we do that? And then Michel already mentioned there was an accident in the Mont Blanc tunnel, but there were several accidents in Europe. Also, we had dramatic fires in the Tauern tunnel. And the European Union decided that tunnels which have lots of traffic in have to get a second tube. And they wrote a guideline, more or less a directive, that in whole Europe there must not be any tunnel with a bidirectional traffic if there is a certain amount of traffic in. And this has to be fulfilled till mid of 2019. Okay, as we have lots of tunnels, we had a huge job to start because all our tunnels were built in the early, let's say 30 years before, with a single tube. Now it came up, all those tunnels need to get a second tube. And we said, let's use this really good opportunity to go from the second tunnel which we built through the cross passages which we have to build because there is a directive that there has to be an escape way every 500 meters, is fixed by the European Union. Okay, when we build these cross passages, let's go to the first tunnel tube coming from the back side. We will never have this chance again. Coming from the back side, and let's take the material out, the old shot grid, 30, 40, 50 years old, the bolts, the wire mesh, the inner linings, the membranes, and let's make research on all these tunnels which we have to build right now till 2019. And let's see if the material which was used is long-term stable. And if yes, perfect. And if no, we can detect where are the problems with these materials. This was one point. And maybe we can build the tunnels in another way than they did it 30 years, 40 years before. Because I would say tunneling was very much coming from the stomach, because it's not comparable to mechanical engineering, where I can do finite elements calculations. I mean, we in tunneling are trying to do finite element calculations, and we are doing them, let's say, and we get fine, nice pictures from yellow to blue colors. But is this the reality? And it was Rabčević at our university, at least, who said, you can start to calculate tunnels if you have thousands of measurements, but not before. You can try to have a best guess, but we are not comparable with mechanical engineers who have a detailed material. We have to deal with the material geology, and nobody knows exactly what it is, and it changes from meter to meter. So we took this opportunity to learn from the old. And the outcome then was what I would like to show you. And maybe we have to rethink a bit what we did the last 30 years. Tunnels were built, let's say, 100 years ago with the cross-section, what you see on the left-hand side. So, for example, the Gega line, which is a line between Vienna and a province in Austria, which is called Graz then, was built by stones, backfilled by stone material. And then, you know, we in Austria, we call it NATM. Then the NATM came up more than 50 years ago, where Rabchevich or many other colleagues said, okay, make a shotcrete shell, let it deform, then make it, wait until the deformation has stopped, then bring in your membrane, and then bring in the inner lining to carry all the load, because the idea was shotcrete is a material which degrades, so it is not existing after some years. And if you follow the German guidelines, still available, still valid in Germany, they still say it in this way. They say, you do your calculation and your inner lining based on all your loads, which is coming from the rock around, and you do not consider the shotcrete shell because it deteriorates. So there is no shotcrete shell after some years. And the question is, can we then come, based on the results of our research studies on all these existing tunnels, that we need no inner lining maybe anymore? Or is the assumption which we had 30 years before still valid? The objective of this research was to investigate the stress situation in the inner lining, of course, because this is the line which has to be, or which is exchanged in most of the rehabilitation works. So we should know what is the stress in these linings. I mean, how should we make a static calculation to repair the tunnel? How far are we allowed to open the tunnel? Can we take out 10 meters of inner lining and it's still stable? Or do we have to do it meter by meter because of static reasons? I have to know the stress in the lining first before I can answer this question, even if there are statics done already now. For this purpose, we did the following. We said we approached the old tunnels from the backside through these cross passages, as I said before. Then in situ stress compensation tests were done. I will show you how it was done. We call it flat check tests. And based on all of these results, we tried to do a best case numerical calculation. We know that the geological information is not much better than that was, let's say, 30 years before, because truly spoken, do you know any material model for numerical calculation which is really well fitting to the geology which you have? I mean, most of us are calculating Moore, Coulomb, Hook, Brown in clay situations, chem clay, hardening soil, whatever. But is this material law really meeting the reality? Question mark. The procedure was, we did individual durability tests on the support material, we did investigations on the support elements on site, and then we tried to make it both together in numerics. I just show you a slide where the tunnels which I will report on in this presentation are shown. You see the Pfänder Tunnel on the western side of Austria, built 1975. Adelberg Tunnel, a 13-kilometer long road tunnel, 1974. Roppener Tunnel, 87. Katschberg, 1970. Tauern, also 1970. I go to the eastern part. Bosrock, 80. Kleinalm, 73. Tanzenberg, Ganstein, 70s. So the results which you will see right now is coming out from these tunnels, where the second tubes are right now under construction or are just finished. The directive of the European Union is called Directive 2004/54/EC of the European Parliament in the year 2004, and it says, in any case where for tunnels at the design stage a 15-year forecast shows that the traffic volume will exceed 10,000 vehicles per day per lane, a twin-tube tunnel with unidirectional traffic shall be in place at the time when this value will be exceeded, and it was fixed, should be ready April 2019 for all over Europe. Some countries are following strictly, others are a little bit later, but I think all countries of Europe are working at least on it. I mean, we are a tunneling group here. I don't need to explain very much about the lining, and we saw it also in Michel's slides. Conventional tunnels are normally existing of shotcrete and the inner lining concrete and rock boards and membranes. And what you see is on the right-hand side, the upper slide is showing here we are just right now building the cross passage, and we are approaching the first tube. Then we have to close the traffic for the first tube for, let's say, some hours to break through the cross passage. And in this case, we take out as most careful as we can all the old materials and bring it to the laboratory. What you see is in some cases we cut out blocks of inner lining concrete, we cut out blocks of shotcrete. For the uniaxial compressive strength test, we needed also shear parameters, so we did shear tests in the laboratory to find out the cohesion and the friction angle. The measured strength was compared then with the requirements of actual guidelines. And the next slide shows the uniaxial tests of sprayed concrete samples, so to say, shotcrete, and the required strength of the guidelines. And what you see is, if you look at the Gunstein tunnel, Katschberg, and these are the average values of lots of samples. For example, let's say for the Gunstein tunnel, we have the old shotcrete, 30 years old, has an average 44.7 megapascal. The required shotcrete, which is nowadays a shotcrete strength SPC 35/45, just the naming changed a little bit, is below the limit than the old shotcrete samples have. So the results of these, and it was the case for all the tunnels, not any tunnel showed that there is any reduction of strength of the shotcrete lining anywhere. You might say, yeah, but the water there could be aggressive water. We collected also the water, but the water content is not, I mean, there are some sulfates here and there, maybe some points where they take, let's say, some strength from the shotcrete. But this result clearly shows that what we learned on university, take care, shotcrete will not be existing, will lose its strength after some years, whatever, is not true for the last 30, 40 years. All the shotcrete samples get some more strength, not very much, but over the 30, 40 years, still increase the strength from the value what they had when they were built. So the philosophy to calculate all the load on the inner lining because the outer lining is not existing after some years, at least does not meet the reality after 30 to 50 years. This was clearly documented by this data. Now the question came, okay, did we then, because, you know, the ministry or the clients got a little bit nervous. They said, did we then build the inner lining for the last 30 years for nothing? Yeah, we couldn't answer that at that moment. Okay, further research. Let's try what is the strength of the inner lining at that moment. And of course, just one detail. We wanted to know why can this be the case? And for that, we had to go in the microscope. We have an electronic microscope on the university, so you see this is 2 microns, where what I show. On the left-hand side is a 1-year-old shot grid. And it shows the needles, what you see here. And the right-hand side picture shows a 30-years-old shot grid. You see the needles, they grew, and they are climbed together, they grew, and then it was clear, okay, when this is the development of shot grid for 30 years, it's clear that there is no reduction of strength. Because it grows, it still grows, but nobody knew that before. Let's do that for the inner linings. Our inner lining guideline, let's say, foresees that we have to use a concrete quality of at least C20/25, which is our guideline. Might be different in some different nations, but this is our guideline. And the inner lining samples after 30 years, 40 years show that all the inner lining results are above this line. So it was not only the shot grid, but it's also the inner lining capacity which didn't fall down, but grew up. So good result, both materials have a life cycle time which is at least more than 50 years. 30, 40, 50. And the question mark is, okay, can we extend that now to 100 years? Will it still grow up to 100 years? What we said is it will not fall down immediately after 50 years. Why should it? If there is no change of these circumstances around, why should it then immediately drop down? Or the stress, let's say, distribution has gone already, so the load is there. So there's no reason why it should drop down. Then we went to the boards. We did mechanical tests, chemical tests. We have institutes on the university which are producing steel. So we hand it over to them and say, okay, please check if there is any deterioration in these materials. So they did chemical, structural observation, and failure pattern analysis. What you see is a typical board which we took out from that. And here you see the results of just what is very used to us, of the tensile tests. Tensile tests of different materials from 30 to 50 years old. And what you see is there is a new board, which is the thick line. The thick line is the new board. When I buy a board today, what is the behavior of this board? And you see it's fully in between the materials which we took out, which are very, very old. The Boshook had a better tensile strength. They used a little bit different material quality. The metal engineers, they are able to detect what is this, what kind of material is that. And what they found out, but what it has no relevance for a tunnel engineer, they found out on the left-hand side, you see there's a fine-grained steel. On the right-hand side, the pictures down, there is a little bit more coarse-grained. But the steel industry says, yeah, we changed our, let's say, factory processing so that on the right-hand side, this coarse-grained, if you look in the microscope, because it is 100 microns, the processing changed a bit so that we get very much finer-grained steel boards today. But from our point of view, where we just are looking on the tensile strengths and then on the, let's say, how good can we connect the rock with this steel, there's absolutely no influence. So tensile strength of these steel materials, full available. Not any board showed any problem. Even if it looks rusty, you see the sample what comes out there, it looks okay, old board will not come out with the full tensile strength, is not the case. The membranes. The membranes are, I mean, the question is, are they still watertight? This is the main question for us, isn't it? And is there a friction between the inner and the outer lining? Because this friction should be considered if there is one. The colleagues in the group here will, let's say, confirm that we never know what to fill in the numerical calculation for the friction angle or even the cohesion, because there's a, let's say, a geotextile in the membrane and then the concrete, and the shotcrete has a little roughness. And what should we fill in the calculation? Our first question was, what about the tensile strength? The plastic engineers, which is an own department in our university, they are doing lots of other tests with the plastics. Not of interest for us. They did it also with these materials, but for us the main point was, is it still watertight? Is the tensile strength still there? You see again a new material, the thicker line in the middle of these lines, so the membranes were going from 2. Depending on what material they used at that time, PVC was the most used material in the tunnels. But let's say the sheets of the requirements 30 years before fully meet the results what we have today. So there is no change from that point of view. But at 30 years before, it was not possible to make a really perfect profile of the tunnel. So it was a shotcrete line which was going anywhere this, and the maximum grain size they used was, I would say, from the course, was a 22. We nowadays, or the last 15 years, do not use such a big corn for the shotcrete. So we use a fine liner before we install the geotextile. That's why they some damages on the membranes were seen because of this rough shotcrete lining. There were much more tests done, microscopic analysis, thermal analysis, and infrared spectroscopy. I mean, the report is all in all about 500 pages thick. All of these detailed results are shown there, but these parameters are not of such interest for us than the tensile. The next question then was, I already mentioned, what is the friction angle which we should consider if we have this double lining and there's a membrane in? And that's why we said we have to make a test first for the mechanical resistance of the sheet membranes. Can we find out a maximum grain size which is allowed for the shotcrete, which does not disturb our membrane? And can we find out what is the maximum stress what the inner lining is allowed to bring to the membrane before it disturbs the membrane? In the calculation is clear. Normally we have an inner lining pressure of 1.5, maximum 2 megapascal, never more. But we thought, let's make tests with higher inner lining pressures just to get a feeling where's the limit. For that, we did some tests on a tunnel which was just under construction. We took a shotcrete from this construction site, which is nowadays used, and took this shotcrete then to the laboratory. This mechanical resistance test gives information about the limits of the pressure due to the compressive strength, as I said, before damaging the membrane, on a shotcrete with different roughness. Because in our contracts, we always say, okay, you are allowed nowadays, you are allowed to use 11 as a maximum grain size. Some contracts say 8. Of course, not 22, then was used some 20 years before. From the principle, it's clear, no? Is the shotcrete, then the ceiling support, what I'm talking about. The ceiling support is this shotcrete which is brought in a next construction stage with this fine grain size shotcrete to protect the membrane. And we wanted to know, to get a high life cycle, what is the maximum grain size which we can allow? Is it true that the 8 millimeter maximum grain size is the maximum which we can allow in the future? or is it a higher one? So you see, we did with this construction site directly spraying this in a box, and this box was then brought to the laboratory, was cut in a way that we can do the tests. The grain sizes which we studied here are shown on this slide. You see the one is a maximum grain size of, let's say, about 8, and the other was here with a maximum grain size of about 4 millimeter. The other is just the specification of the shot grid which was used. Now, in order to imitate the secondary lining as real as possible, we built a negative mold. So there is a steel production area which pours the steel in. I don't know the English word for that, but if you have a car, your engine which is in your car is a steel which is poured. And this is an own technology to produce now a concrete which is directly following the shot grid roughness, which is the case in the inner lining construction. Because if you have your shot grid and then you bring in your framework, you pour in your concrete, and your concrete follows exactly your geometry of your shot grid. And that's what we wanted to simulate also in the laboratory. And then the question was, what is the pressure of this inner lining concrete going to the membrane, which is in between to the shot grid? There's the inner lining, the membrane, the shot grid, geotextile in between. And of course, we have to consider the maximum pressure which goes on this membrane in a liquid stage. Because when you pour in your concrete with your framework on the construction site, you have a liquid concrete, and this liquid concrete brings the pressure to your membrane. And this is just the calculation for that. So we have on the one hand side, you see the shot grid, then the geotextile, the membrane, and the concrete. So the picture on the right-hand side down there was the sample finalized, which we got from the construction site, then finalized in the laboratory. With this sample, we made roughness tests, photogrammetric roughness tests, to see what is the roughness of the different grain sizes which you can use in an outer or inner lining. The roughness was pretty the same. And then we went to long-term tests, because the tunnel which I mentioned before, the Brenner base tunnel, has, for example, an overburden of almost 2,000 meters. So we have a temperature down there, a rock temperature, between 50 and 60 degrees. So the question was, if we build it like we always do it, is the membrane able to withstand the high temperature and the stress? That's why we did these long-term tests, 1 month, under high temperature, rock temperature 60 degrees, pressure uniaxial, and then let's see what happens with the membrane. And the load what we brought to this sample was 2 megapascal. Coming from the calculation, 2 megapascal is the typical inner lining pressure which we normally dimension the inner linings for. And the result was, you see the temperature profile on this staired curve. We went up to the 60 degrees, what we expect in the tunnel, and we used the different grain sizes for the shot grid. The different grain sizes had now the result of different deformations, and the interesting result was that the temperature has an enormous influence to the life cycle time of the membrane. Doesn't matter if it is only 2 or 1.5, whatever megapascal. So if you have a tunnel deep situated, where you expect high temperature, take care on the material which you use. If you use these normal membranes, PVC, or even PE, we tested also PE here, polyethylene, then it's really getting damages even after 1 month, because the temperature is very, very much important. The grain size, if you use a 4 millimeter, 8 millimeter, 11 millimeter for the maximum grain size for the membranes, had no influence. The damage came just by the temperature on the long term. We tested it also with a 5 megapascal to get the results a little bit more extreme. You see here a membrane tested with 60 degrees with 2 megapascal on the left-hand side. Even there was of course a geotextile in between. And you see that we have damages in the membrane with the 2 megapascal, where when we have 20 degrees Celsius with 2 megapascal, there's almost nothing on the long-term test. This was quite important result for us for the deep situated tunnels where we have these higher temperatures. And then we did another test. We wanted to see a maximum stress which can be brought to the membranes before they, let's say, get damaged. And therefore, we built such a vessel where we were able to bring up also 20 bars, just to figure out the limits. What can a membrane withstand if I pour in a concrete? The concrete here was the liquid poured on the membrane, and we brought up this high stress just to find out, even if you never build an inner lining with 20 megapascal, just if you maybe go in a hydropower construction, then the situation is different. Then you might reach these high stresses. You see that the tests show no damage caused to the membrane if we use a geotextile with 500 grams per square meter. It is high if we use, and you can use different geotextiles. There are geotextiles on the market available from 100 grams per square meter up to 500. But if we use a 500 grams geotextile, you can even press with 20 bars. And normally, in practical life, we never have more than that. We get no damage on the membrane from this point of view. This was, by the way, under normal temperature, 20 degrees. The next question was done, a shear test. A shear test was done to find out these parameters for the numerics for the future. So we built up a sandwich layer and wanted to know what is the capacity, what these membranes and including the geotextile can bring. For that reason, we had to go to Germany because in Austria we don't have such a big shear test available. Germany, from the old mining research departments, they have big shear tests. So we were able to bring our sample, which was then 50-50-50, big, and had the membrane in between in the geotextile, brought it to this shear machinery, what you see on the sketch down there, and were able to make a really fine shear test with that. At the TU Graz, we did another shear test, but we in Austria just have a 30-30-30 sample size as a maximum available. But just to compare the results of different shear tests, this gives you just the forces which we did. But you get these slides, so you can read that if you want. The shear rate which we did was 40 millimeter per hour, so very slow shearing, like in a real tunnel might also be. If we bring in the inner lining too early, we will have shear between. Just a slide from these shear tests. This is the big shear test, and the right-hand side photo shows the movement of these two blocks. And then we did the following. One time on the left-hand side, we didn't fix the geotextile and the membrane. We just had the sample, put the geotextile in, the membrane in, and the concrete above it, but no fixing. And the other was the more realistic what is done in the tunnel, because we fix the membrane. Because we have to, anyhow, to install the membrane and the geotextile in the tunnel, so we fix it. And we wanted to know, is there a difference? The right-hand side, as I said, is the fixed one. And I just show you the movement on both membranes. Right-hand side, fixed one. And of course, you see the membrane is pulled with the inner lining out of this by the shearing. The geotextile keeps where it is. On the left-hand side, the membrane does not move with the concrete block. So there is much more stress in the membrane on the more realistic test, which is the right-hand one. And the question is, how can we do that? Not to get such a high shearing in the membrane, how could we install the membrane in future? Because this would be the much better one. The shear test's results are the following. The grain size didn't have any influence. There were just, let's say, if you have a peak in the shot grid and you see the cone, yeah, then this cone is the one which damages your membrane, because it keeps hanging on this cone, very, very clear. But the shear test results you see on this diagram, they were pretty much comparable. And the friction angle of the 30-30-30 shear tests and the 50-50, which we did in Germany, were very much comparable. And we can say we have a friction angle for the membrane to be considered with, as far as I remember, 17 degrees. I have it in my conclusions, but I think the number was 17 degrees, which we should consider. In many calculations, we see there's absolutely nothing considered. Yeah? There's a short grid or outer lining, inner lining, membrane in between, and there's nothing of shearing considered in the calculations, which is clearly wrong. These are the results then shown on a typical Mohr column. Yeah, the connection between the membrane and the shot grid, of course, causes a shift of the relative movement from the membrane into the secondary lining. In consequence of the normal and the shear stress, the sheet membranes are damaged. What we learn out of that is never build the inner lining as long as you have movements of the outer lining. So what we fixed is, we had, I mean, the idea of the old engineers was already bring the inner lining 1 year after you have built the outer lining, if, let's say, you have time enough. If not, you cannot wait just for this reason. But now we see, if you do it, you get a shearing in between, which damages your membrane. So from the life cycle point of view, we have to wait until there's no deformation of the outer lining. No, we fixed means 2 millimeter deformation in a month, which is even quite high, but the client said, please don't write 2 millimeter in a year, because then, so our guideline now says this limited value, even if 0 would be the best, of course, from the life cycle point of view, because then you have no, let's say, danger that your membranes are then disturbed. Now, all of that were laboratory tests. Now, let's jump into the practical field. And we found a company, again in Germany, which was able to fulfill our request to measure the inner lining stress. Now, the idea was we have to do that in the existing tunnel tubes, where we are clear that these existing tunnel tubes will be renovated. The procedure I forgot to tell you is the following. We build now the second tubes. When the second tubes are ready built with all the cross passages, we do the renovation works of the old tubes. So in 2019, all the tubes are renewed. Have 2 tubes. The tunnels have then 2 tubes. The one which is the new, and the old one is rehabilitated. And in these tunnels, we were allowed to make cuts into the inner linings. The client said, okay, test it to find out what is the stress in the inner lining. We always did that in the middle, in the upper part, in the roof, and on the side wall. Because here we have the maximum stress concentration, which we know quite clearly from the calculations. So we cut with a saw into the inner lining, but we first fix some measurement points, and you see it on the right-hand side upper photo. There are measurement points where this company, which helped us in this regard, was able to make a surveying of the deformation of these points on the micrometer. After the cutting, if there is a stress in, you will get a deformation of your cutted slot. And the next job was then to blow up the slot again to the original size, and coming from this result, blowing up the slot to the original saw cut, we know the force in the inner lining. And this was done in several, in all the tunnels which I showed you before. And it was very clear after the tests were fulfilled that in anhydrite, which is a swelling geology, you get a stress in the inner lining. And this was measured very clear. And in all the other tunnels, where we have limestone, marbles, granites, whatever, what is not a swelling ground, we have absolutely nothing. We nowhere measured outside these swelling rock types any stress in the inner lining. After that, we did the numerical simulations because we wanted to see how is the load, or what procedure must happen to get inner lining stress. So we did what our professors 30 years before told us. There is a deterioration of the shotcrete. Because of that, dimension your inner lining on the full load. So we did nothing than that in our numerical calculations. We got all the reports from these tunnels, geology, what they did at that time. And then nowadays it's possible to build everything in one numerical model. So at that time we used Sophistic, because this is very much used in engineering, in design consultants' offices. So we build in the outer lining, the inner lining in between the membrane with the now 17 to 22 degrees, and used the real geological, let's say, reports which were available from all these tunnels, and then we started to calculate. First, left-hand side upper photo, forces in the shotcrete lining after construction. We clearly followed the construction sequence which was built. In that case, there was a temporary invert, so we also built it in a temporary invert in our design. Then we installed the inner lining. At that time, no stress in. And then we did a degradation of the outer lining, 10%, 20, 30, just to see at what time do we then get which size of inner lining stress, which we then should measure. As we measured nowhere any inner lining stress, just in the swelling grounds, it was also clear from this calculation the outer lining must be complete intact, because we measure no let's say, inner lining stress. And this fits very good to our results of the shotcrete samples, which showed that the UCS is growing up. Yeah, the summary, therefore, is This research showed that the support function of the primary support is unaffected, let's say, after 30 years. The research showed no reduction of a technical lifetime regarding the strength of any of the support elements which were tested, and we tested all of them. The stress measurements of the inner lining indicate that the bearing capacity of the outer lining is full intact. The shear parameters of the membrane should be integrated in static calculations. The resulting shear angle, when you use a maximum grain size in the short grid of about 8 millimeters, is then between 17 and 22, very clear shown. The testing results of the stress measurements at the inner lining and the simulation show that in rock with good geotechnical parameters, only low or even no stress can be detected in the inner lining. Only in areas with swelling rock, higher stress can be measured and also calculated. Fits very good together. Concepts in which the outer lining is part of a permanent support element should be more and more considered. Why do I bring this presentation in this forum? It is highly environmental impact relevant, because if we can reduce our thickness of our linings, we can make the tunnel breakout diameter much smaller, because our minimum inner lining is for the moment 30 centimeters written in the guideline. So if we can save 30 centimeters on both sides, it's 60 centimeters on the diameter. If you calculate that for tunnels which are, let's say, 10 kilometers long, or what we are doing, what I mentioned before, we are building 200 kilometers, and if I can save that, it goes directly in the environmental impact study, and is a really major resource-efficient topic if we rethink the philosophy, what we learned 30 years before. And we should do that because, I mean, of course, the older guy says, would you say we did do a mistake? No, nobody knew. But now we have documented results, and we should consider that in further designs. That's what we say. We didn't say anybody made a mistake. That's what I wanted to tell you before the lunch. Thanks for listening, and I'm happy for your questions.